But for this week, we're going to be doing Lewis structures. And we did these in Intro Chem, but there is some new things for us to think about here. In fact, when I cover this in Intro Chem, I always sort of say, this is like one of the few topics where I'm always a little bit weary of students getting tutoring in Intro Chem. Because in Intro Chem, we stick to the Octet Rule. We don't go past that. I mentioned that you can, but we don't in Intro. And so now what we're going to do is expand the octet. We're going to look at formal charges. And those are things we didn't talk about in Intro. So occasionally when I have students from Intro get tutoring, they come back and they're like, wait, this is confusing. Why do I have 6 bonds around sulfur? So anyway, now we're going to put all these topics together. So first we have to go through Lewis structures, and then we'll talk a little bit about bond energies, and we'll look at formal charges and expanding the octet. And then next chapter, we're going to add to it some geometry, tetrahedral shape versus trigonal pyramidal. And then we'll look at how that plays into intermolecular forces, which are the forces that hold molecules together. Okay, so the first thing is when we were covering chapter 9, we had to understand the valence electrons. And what we said for the valence electrons, it was the electrons in the highest occupied shell. And so when we were doing this in Intro, we said, okay, alkali metals always have 1 valence electron, hydrogen 2 is also just 1. I meant TOO, not TWO. So hydrogen also has 1 valence electron. The alkaline earth metals, right, 2 valence electrons, helium as well. I said for the purposes of electron configurations, I always think helium should be over here. Then when we go over to the right side of our periodic table, when we get to the P block elements, right, the boron and aluminum, they have 3 valence electrons, group 3, carbon family is 4, nitrogen is 5, oxygen 6, halogens are 7. And then the noble gases have 8, except of course helium, which is only 2 because it's 1s2. And we know that there's something very satisfying about that noble gas configuration because those elements are highly unreactive. They are very stable. They have what everybody else is looking for. So there's something very special that happens. I call it like a stability switch, and it clicks on right at that S2P6 configuration. So we learned in the beginning, halogens, right? They just need 1 more electron to fill out that valence S2P6, and then they're happy. So they're always -1. And then the alkali metals, they have only 1 valence electron. They want to always lose 1 valence electron to then have core S2P6. So we've seen some of this before. And then what we added to that for Chem 1 is what do we do with the transition metals? And we won't do a lot of that with the Lewis structures. So we won't have to worry about that, but just to repeat something we saw on Tuesday, if you're looking at the valence electrons for a transition element, it's everything in the highest occupied S and any unfilled D. So like I think one of the examples we looked at on Tuesday was iron, right? Iron has 1, 2 valence electrons in the 4s2, and then also 1, 2, 3, 4, 5, 6, 3d6 valence electrons. But then we said with zinc, right? Zinc has a full 3d shell. So then if it's a full 3d, then it's no longer valence, it acts as core. So zinc only has 2 valence electrons. But what we're going to need when we look at our periodic table, when we start doing Lewis structures, is we're going to need a quick grab of the number of valence electrons. Just something where I can look at the table and say, yep, it's got 4 valence electrons. And we won't be doing that with the transition metals, right? The transition metals just don't, they don't behave. They don't follow all the rules. So we're going to need to remember alkaline metals, 1 valence electrons, alkaline earth metals, 2 valence electrons. And then over here, we've got the 3, 4, 5, 6, 7, and 8. So that's first, valence electrons, right? What we're looking at again are the electrons in the highest occupied shells. We're going to stick with Lewis structures for just the representative elements. So again, no transition elements will show up here. And every element wants that octet rule, right? Octet meaning 8, where they have that S2P6 configuration. How they get to it, right? That depends, right? If it's a metal, it's going to engage more than likely in ionic bonding. So it's going to lose electrons to then have an S2P6 core. It loses all the valence. If it's a non-metal, well, then it's either going to gain electrons to fill out the S2P6 configuration, or it's going to engage in covalent bonding, which is sharing electrons. But again, the goal is to get that S2P6 configuration. So every element, the representative elements, again, transition elements are out the window here. they follow the octet rule for 8. Now, the exception here is if you look at, this makes total sense, when you look at the periodic table, remember in row 1, right, we only have an S subshell. So there is no 1p6, right? So hydrogen can't follow the octet rule because there's no octet to have. So hydrogen follows what's called the duet rule. All right, so it's just because the hydrogen has the exception, it's 1s1 configuration. In order for it to feel like a noble gas, it wants to feel like helium, which is a 1s2 configuration, which is why hydrogen follows duet for 2, because that's all it can take. It can't have a p6 because there is no p in the first energy shell. All right, so that's the first thing. Everybody's looking for that noble gas feeling. All right, now how do they get there? So as I mentioned, if it's a metal, they're typically going to lose all of their valence electrons to then have a very stable core. And then if it's a non-metal, the other way, right? So when we start here with sodium, sodium would have a Lewis dot structure. We use a dot to represent every valence electron, right? Just the valence, because that's the important part. And so sodium would start out with 1 valence electron, so 1 dot. Magnesium, group 2, alkaline earth metal, has 2 valence electrons, so 2 dots. Now, if I wanted to do aluminum, if I look at aluminum on my periodic table, aluminum is group 3, so it should have 3 valence electrons, which it does. It's an S2P1. So it's going to need 3 dots. Now, textbooks will do this a little bit differently. Some textbooks will say, okay, write your element symbol and then put a dot on each side, right? And then once you get to the 5th side, now you start to pair. So here's what the Lewis dot structure is trying to mimic. When we were looking at orbital diagrams, we would have drawn a box for the S, and then the P would have had 3 boxes. So there are a total of 4 orbital spaces here, right? There's the S subshell and the P subshell. That P subshell has the 3 p orbitals, right? The X, Y, Z. So there's a total of 1, 2, 3, 4 orbital spaces. So when I go to do a Lewis structure, I have my element symbol in the middle. And then I have these sort of 4 orbital spaces, right? So if I were thinking of this as like a box here for 1 orbital and another box and another box and another box, there's my 1, 2, 3, 4 orbital spaces. So at the moment, we're stuck with working on top, bottom, left, right, nothing in the corners yet. Okay, so just top, bottom, left, and right. So when I do a dot structure, in my mind, I think it should match, the Lewis structure should match the orbital diagram. And so here's what happens. If I were looking at aluminum, aluminum is an S2P1. So if I were going to draw the dot structure, I would draw it with a pair and a single, right? Because there's the S2 and there's the P1. Now, notation here, like an asterisk, there is nothing that says the S is on the right and the P are the other 3. And there's nothing that says the S is the one on top and the P is the other 3, right? That is all up for whatever, however you want to draw it is fine. But in my mind, when I draw the Lewis dot structure for aluminum, I should show that 2 of those electrons are paired and 1 of them is a single. That's in my mind. Other textbooks will say, you know what, it doesn't make a difference because there's 3 valence electrons. We know that. So we're just going to draw 3 dots. And the reason why it doesn't matter is because when aluminum engage in bonding, right, it's a metal, it's going to lose those electrons anyway. So when we get to the aluminum ion, we just have it with no dots left because all the electrons, the 3 dots, have been given away. So these 2 right here, those 2 Lewis dot structures, if you want to draw it like the orbital diagram shows you to do it, which is a pair and a single, great. If you want to just draw it with 3 dots, also great, because the point that we just have to know is that there should be 3 dots, right? As long as you know that aluminum has 3 valence electrons as an atom, right? It has if we look at the periodic table, aluminum, right? There's a neon core, and then it would have the S2 and the P1, so 3 valence electrons. So as long as you draw 3 dots, it doesn't really matter how you do it, all right? Again, don't do the corners, just do top, bottom, left, or right. Now, if I do sulfur, here it gets easier. So sulfur in the oxygen family has 6 valence electrons. It's an S2P4, right? Neon core, and then past that, a 3s2, 3p4. So 2 plus 4, there's a total of 6. So this is kind of where this system over here, putting one on each side and then pairing, this is where it works, right? So for sulfur, I have 1, 2, 3, 4, and then pair 5 and pair 6. And if I drew my orbital diagram for sulfur, we said it's an S2 and then a P4. And if it's a P4, we have a pair and 2 singles in that P subshell. So this matches, right? 2 pairs, 2 singles. So this way, it really don't stress about that too much. But the thing you need to know here is that there should be 6 dots. Now, sulfur, like everything else, right, wants to look like a noble gas. And neon, it's an S2P6 group 8, right? So there's 8 valence electrons. There's something very satisfying about having 4 pairs of electrons in your valence shell. So that S2P6 is, there's just, like I said, it's like a stability switch clicks on. So everybody's trying to look like that noble gas configuration. So sulfur, right, we can see probably wants to either take 2 covalent bonds sharing electrons, but we'll talk about that in more detail. 2 bonds would help it complete the octet, or it wants to completely steal 2 electrons from somebody else, right, and pick up those 2 missing dots to finish out the octet. So the 2 types of bonds, like we've already talked about, right, we have an ionic bond where you have ions. So electrons have been transferred, metal loses, non-metal gains. There's an actual transfer of electrons. The covalent bond happens when you have a non-metal and non-metal. We remember that from nomenclature, where now both elements want to gain electrons, so neither one wants to give up. So instead, what they do is they share. And so now that we have a better understanding about those outer valence S and P orbitals, now what we can kind of envision is those S and P valence orbitals overlapping. And when they overlap in space, they can share their electrons. And that's what we're going to lead into in the next chapter when we start looking at geometries. Because what we're going to learn is the whole S and P rigor, like that shape, it doesn't really stay that shape anymore. So I remember when I learned it, I was like, wait a minute. Okay, so the S and P is kind of out the window because they hybridize. Anyway, so that we'll get to that to the next chapter. But what's important now is if it's an ionic bond, like we learned in nomenclature, that's going to be metal and non-metal, and the electrons are transferred. Metal loses, non-metal gains. If it's covalent, is when the electrons are shared between non-metal and non-metal. And we can use Lewis structures to illustrate both types of bonding. Now it's going to be way more helpful, and you'll see this when we look at covalent bonding. We'll start to be able to understand, like, okay, the carbon oxygen, for example, how is carbon monoxide stable, carbon dioxide stable, carbonate, polyatomic ion, oxalate, right? These are just carbon oxygen, either compounds or ions. How are all of those possibilities stable? It's not like sodium chloride, right? It's just NaCl. That's the only possibility. So Lewis structures are way more helpful when we do covalent bonding, but we can use it to illustrate ionic bonding. In my mind, I kind of think, well, it doesn't really tell us anything we don't already know. So what's the point? But we're going to look at one of these, right? So let's say we were going to use a Lewis structure to show the bond that would occur between sodium and oxygen. So first thing we're going to do is start with the atoms, right? So sodium, symbol Na, and it's an alkali metal, group 1, so it has 1 valence electron. And then oxygen, group 6, just like sulfur, has 6 electrons. I'm going to put the 2 pairs on the bottom and the 2 singles on the side, and you'll see why. So that's how it starts out. We start out with the atoms. Then what we're going to do is we're going to show that because this is metal and non-metal, there's going to be a transfer of electrons. Now, we're not going to move them yet. We're just going to show what happens. That 1 valence electron for sodium, sodium really wants to release that because what is underneath that is a nice neon core, right? So sodium has this valence electron, but underneath it, it has that S2P6 core, which is really stable. So sodium says, you know what, I'm going to get rid of that valence electron, but it only has 1 to give. It can't give up 2 because then it would be breaking into that neon isoelectronic, that configuration. It doesn't want to do that. So sodium's going to give 1 electron to that 1 sort of empty spot for oxygen, but clearly that's not going to do this, right? We know that sodium oxide is not NaO, right? So I need another sodium with another valence electron. And I'm going to show that that valence electron also is going to go to that second empty spot for the oxygen, right? So the electron transfer always from the metal to the nonmetal, right? Metals want to empty out their valence shell, nonmetals want to fill it. And now what we can do is part 2 is show what the ions look like. So now sodium, both of them, so there's 2 of them, they've both released their valence electron. And so they don't have any electrons in their valence shell. And so we show that. We show that the shell now, that outer shell, which used to have an electron in it, is now empty. And we're going to say it's +1 because it's lost an electron. Then for the oxygen, oxygen now has 2, 4, 6, and 8, right? It has picked up those 2 electrons that it really, really wanted. It now carries a -2 charge because it has 2 extra negative particles. And now when I look at oxygen, it looks just like neon in terms of the electron structure. And so when we were learning nomenclature, we learned that because sodium is always a +1 and oxygen is always a -2, we do the crisscross, and we knew that the formula had to be Na2O. So you see, for me, with Lewis structures and ionic compounds, to me, it doesn't tell us anything we didn't already know, right? We need 2 sodiums and 1 oxygen here to make this work. The metals want to empty out their shell. They each have 1 to give. Oxygen wants to fill the shell with 8, so it needs to pick up 2. So it has to have 2 sodiums to make this all balance out, right? So to me, it looks like, okay, we can do that. We can show the transfer of electrons. That's the key here. Because it's an ionic bond, we're going to show the transfer. That's going to change when we look at covalent bond. And instead of transfer, we're going to look at overlap. All right. Now, the next part of this is it says the formation of sodium oxide, from sodium element and oxygen element. When I form this ionic compound, it is highly exothermic, right? So we release a ton of heat when this happens. And this is due to what's called a lattice energy. So the energy of the structure, the salt structure. And it's exothermic because if you think about it, sodium ion is nice and stable, noble gas configuration now in the core. The oxygen ion, also nice and stable, noble gas configuration as well. And those electrostatic forces that hold those ions together are very stabilizing. So that lattice energy, we took unstable elements that were separate. I mean, oxygen, diatomic, not that unstable, but sodium metal, highly unstable, right? And now we've made this more stable salt, the sodium oxide. And the lattice energy is exothermic when that happens, when you get a stabilizing effect from making these ions, and then having those ions come together. It'll be more exothermic the smaller the ions are, because the better packed that together they can be, the better they can feel the positive and negative charges, right? And also more exothermic, the higher the charge on the ion, meaning absolute value. So like a +2 ion has a better energy stabilization with a -2 ion versus a +1 and a -1, right? The higher the charges, the +2 -2 versus +1 -1, the higher those charges are, the more exothermic that lattice energy will be. All right, I always felt like, okay, well, +2 -2 just holds together better. It's a stronger charge than +1 -1. All right, so that's just first talking a little bit about ionic compounds. So if I use that information and then answer this question here. All right, so let's say I've got lithium chloride, and then beryllium oxide. And I say, okay, one of those has a melting point of 605 degrees Celsius. The other one, like over 4 times as much, right? 2,507 degrees Celsius. So which one has the higher melting point? So the lattice energy that we were talking about up here, the thing you want to take with you to answer this question is the lattice structure, the salt structure, where the ions can be closer together and the charges are stronger. The more difficult it will be to break up that structure. The more exothermic the lattice energy is, the more difficult it will be to destabilize it, right? So when I look at lithium chloride and beryllium oxide, first thing that I notice is the charge. Like lithium is +1, beryllium is +2. And then when I come over to my nonmetal side, oxygen is -2 and chlorine is -1. So if I look at my charges here, lithium chloride +1 -1, beryllium oxide +2 -2. So, excuse me, so if we're just going on charges, we expect the lattice energy for beryllium oxide to be more exothermic. This is a more stable salt crystal. It's going to be more difficult to melt it and break it apart. The other thing then I can look at is the size. Lithium ion and beryllium ion should be pretty similar in size, right? They're in the same row. And then over here, I've got oxygen and chlorine. Oxygen is a whole energy shell smaller. So the ion size, the smaller ion, would go here for the oxygen. So for beryllium oxide, it's got two things going for it. It has the smaller oxide anion, and it has the higher charges. So +2 -2 versus +1 -1. So because of that, it is going to have the higher melting point. It's going to be harder to break up the beryllium and oxide ions because the charges holding them together are stronger. And those ions can be more tightly packed together because they're smaller because of the oxygen. All right. So higher melting point, right? That's what we want to look at. We want to look at ion size and the charges, right? So for this one, opposite, we want which one has the lower melting point. So opposite trend, we're looking at sodium chloride and cesium chloride. Well, both of those are +1 -1 salts, right? Alkali metal with a halogen. So the charge difference, there isn't one. So we don't have to look at that. Like up here, we had to think, oh, well, the charge plays into this because one of these +1 -1, the other one's +2 -2. These, however, both of these compounds are +1 -1. So the charge, they're the same. So that's a wash. So then what I look at is the size. And both of them, the anion is the same, but now the cation is different. So we look at that, the trend on the periodic table that we learned in the last chapter, sodium, right, is going to be much smaller than cesium. So if I'm looking at this one, the cesium chloride has larger ions, well, the cesium specifically. So this one is going to have the lower melting point. Right, the larger the ions are, the more difficult it will be to pack them closely together. And that means the easier it will be to break them apart. So if you have tiny ions, they can pack together really nicely, and it'll be very difficult because now those electrostatic + charges can be really effective because the ions are really close together. And then it'll be more difficult to break up the ion by melting it, or break up the compound, sorry, by melting it. So in this case, because cesium is a larger ion, it's going to be easier to break it up. So that when you start thinking about heating both of those salts, the one that melts first is the one that's easier to melt, right? It's easier to break it up. All right, now with covalent compounds are obviously completely different. We don't have any ions in covalent compounds, so we don't have to worry about charges anymore. So we're going to look at very simple diatomic molecules first. So these are all part of Hofbrinkel, hydrogen, nitrogen, oxygen, and fluorine. And we want to look at the Lewis structure for those molecules. And then we're going to talk about whether the bond would be polar or nonpolar. All right, so first thing, if I look at hydrogen with its 1s1 electron, and then another hydrogen with its 1s1 electron, rather than the hydrogen on the left giving an electron to hydrogen on the right, that doesn't make sense because these are the same elements. So neither one is going to give to the other. So what they do here is imagine this is hydrogen's 1s space, and imagine this is the other hydrogen's 1s space, right? They overlap. They just kind of push them right on top of each other. And that shared space in the middle is called a bond, right? That's where we make a bond. Now, one bond is always 2 electrons. Now you can have a double bond, which means you've got a total of 4 electrons, or a triple bond, which is a total of 6. But each bond by itself is 2 electrons. And those 2 electrons, right, they're in shared orbital spaces. Those electrons are being shared. So the hydrogen on the left feels now like it has a 1s2 configuration. And the hydrogen on the right also feels like it has a 1s2 electron configuration. Remember, this is the duet rule, right? Hydrogen maxes out at 2 electrons. because it has that 1s2 helium feeling. All right, so that's the hydrogen bond. That's what that looks like. When I look at fluorine, I'm going to put fluorine all the way over here on the right. Fluorine comes in with 7 valence electrons because it's group 7 halogen. So I would have 7 dots. And both fluorines, same thing, 7 dots. All right, and it's going to be sort of the same idea. The only thing that's different here is that the fluorine is going to follow the octet rule like every other nonmetal. Hydrogen, again, the exception with the duet rule. So I look at that shared orbital space, the overlap, right? Here's my bonding pair of electrons. So now when I look at the fluorine on the left, it feels like it has 2, 4, 6, 8 electrons, right? So octet rule satisfied. All right, the fluorine on the right, 2, 4, 6, also 8. So the 2 electrons that are in the shared space, they get credited to both elements there. So fluorine also held together by just a single bond, right? Now, if I look at oxygen, oxygen we said comes in with 6 valence electrons. So 2, 4, and I'm going to use pencil for the last 2, actually for one of them. So here's 5, and then here's 6. All right, so there's my 6 dots. And then I'll have another oxygen over here, 2, 4, 5, and then I'll do a pencil for number 6. All right, so when I look at the shared space, right, here's my orbital space for oxygen, here's mine for the other oxygen. And I can see here that obviously a bond is going to form between those 2 electrons that I drew in the middle. But now if I look at it, oxygen on the left, 2, 4, 6, 7, not quite done yet. And the same with the oxygen on the right, 2, 4, 6, and 7. So oxygen isn't held together by a single bond. What will have to happen here is that valence electron that's not partnered on each of those oxygens, what's going to happen is it's going to move into that shared space, and we're going to end up with a double bond for the oxygen, right? And now when I look at it, that oxygen on the left came in with 2, 4, 6 electrons, shared 2 with the other oxygen. So now it has 2, 4, 6, 8. The oxygen on the left, same thing. It comes in with 6 electrons, right? 2, 4, and 6. And it shares 2 with another oxygen. So now it feels like it has 2, 4, 6, 8. So again, octet rule is satisfied. But what's different here is that this is going to be a double bond. All right. And then with nitrogen, nitrogen has 5 valence electrons. All right. So again, I'm going to use my pencil because I know where this is headed. And you can probably guess this, right? If you think, okay, nitrogen has 5 valence electrons. Everybody wants the octet rule, 8. So if it has 5, it needs 3 more. And the other nitrogen looks exactly the same, right? It has 5, it needs 3 more. So you can kind of guess. Oxygen had 6, needed 2, so it took a double bond. Nitrogen has 5, needs 3, so it's going to take a triple bond. So these 2 that I wrote in pencil on each of those nitrogens, I'm going to move those to the middle. All right, and then I can get rid of these, the ones that I drew in pencil, because I knew they were going to go away. And nitrogen, when we look at it, is held together by a triple bond. So the nitrogen on the left, I'm going to draw the circle, nitrogen on the right. And what I have in the middle is a triple bond. All right. So now the nitrogen, 2, 4, 6, 8 total in its circle. So it fills the octet rule. It came in with 1, 2, 3, 4, 5, but then is sharing another 3 with the other nitrogen to finish out the octet. So the follow-up question to this was, okay, now that we have the Lewis structures for those binary compounds, would the bond between them be polar or nonpolar? So what does that mean? Polar and nonpolar, terms that we saw back in intro. It's basically saying, yes, okay, those electrons are shared. We talked about that, it's covalent. Covalent means the electrons are shared. But polar, nonpolar, what that's saying is, okay, well, how are they shared? Are they shared evenly or unevenly? And when you have a bond, whether it's double, triple, single, whatever, between the same 2 elements, then both of that those elements are going to have the exact same electronegativity, right? We learned that back in the last chapter. Electronegativity is the desire to gain electrons. So this nitrogen on the right has the exact same desire to gain electrons as the nitrogen on the left. The fluorine on the right, same as the fluorine on the left. So in my mind, I thought of this like playing tug of war. So you have the flag in the middle, right? Let's pretend the flag is the extra electron. This fluorine is pulling really hard for that flag, and the fluorine on the left is pulling with the exact same strength, right? So they're both pulling as equally hard on that last electron they need to finish out their octet. So in that case, if you could look at this on an electron microscope, you would see that this pair of electron, the density of it is shared completely evenly between the two fluorines. And the same is true with the double bond for the oxygen and the triple bond for the nitrogen and the single bond for the hydrogen. In this case, because, where am I going to put this? This is going to be nonpolar. All of those four compounds that we looked at, they're all nonpolar. What we expect is there should be completely even sharing of the bonding electrons. All right, and that happens when you have the same nonmetal and nonmetal bonding together. All right, so really what this comes down to is the electronegativity difference, and we'll see that in the next chapter, in the next section right here. But I kind of liken this again to a game of tug of war. And so you've got this flag in the middle, which is the extra electron they're both looking for. And one of them is pulling really hard one way, and the other one is pulling equally hard the other way. And so the flag just stays right in the middle. So that is an even sharing of electrons, and that always happens when you have the same two nonmetals that are engaging in the bond. So all four of these examples here are nonpolar. All right. Now, what if I change it just a little bit? All right, so let's say instead of an FF bond, we do a BRF. All right, so if we have Br, 7 valence electrons, and the fluorine also 7 valence electrons, both of them also just want 1 electron, just like the F2 bond. Same thing's going to happen. They're going to create a single bond. And so when I look at the fluorine, it has 8 electrons after it bonds with bromine. The bromine now also has 8 electrons after it bonds with the fluorine. But now if I look at my sort of, pull the flag, right, tug of war, see what happens. I'm thinking about this being in the middle. Fluorine is our most electronegative element, all right? And the electronegativity values, they're given, it's a scale from 0 to 4. So fluorine has a value of 4. Bromine is only 2.8. So bromine's going to pull, but not nearly as effectively as the fluorine. And so what's going to happen is that that shared pair of electrons in the middle doesn't stay perfectly in the middle. The flag's going to go more towards the fluorine side. And since the flag that we're talking about is an electron, what happens is the electron, obviously negative particle, because it's not evenly distributed, it's going to rest more on the fluorine side, and it's going to create an electron-rich side and an electron-poor side. In other words, there's going to be this offset. It's not going to be perfectly even. And the negative, this is this curvy D thing, looks like a music note or something. It's called a dipole. And the dipole, the reason why you don't put like +1, -1 is because this isn't a transfer of electrons. We're still just sharing, but the sharing isn't even. So we have a negative side, which is where the electron really is sort of more going on that side. And then the positive side, which is where the electron is leaving from. So bromine isn't holding on to that electron that it brought into the bond, as well as the fluorine is trying to grab it away from it. Again, not a full transfer because bromine is still pretty strong. It's still holding onto that flag pretty well, but not nearly as well as the fluorine. So it creates a negative side and a positive side. And then to me, when I was learning this, I was like, oh yeah, just like poles on a magnet, right? We learned that back in what, elementary school or middle school, that a magnet has a positive end and a negative end, just like this, right? So that's why this is called polar, because you have an uneven sharing of the electrons in the bond. Right, and that happens typically when you have 2 different nonmetals. Now that is an oversimplification of the definition for polar. Because technically what we want is we want an electronegativity difference that is between 0.04 and 2. And so what that means is if I look at my value of electronegativity for fluorine, which is 4, and bromine, which is 2.8, the difference there is 1.2. So you'll see this, it'll say, okay, the difference in the electronegativity here is 1.2. And so if that difference is more than 0.4 and up to 2, that means it's going to be polar. If you go past 2, then we're kind of getting into the section on being ionic. All right, because then that means one of them is way more stronger than the other, so there's probably going to just be a transfer. And if it's less than 0.4, that means they're pretty much pulling at the same strength. So overall, we're just going to say it's nonpolar. I always like the really simple definition, right? If it's two nonmetals that are the same, makes sense, no poles. If it's two nonmetals that are different, we're going to have polar. But the problem is that carbon hydrogen, which is, you have a whole year of chemistry devoted to organic compounds. Carbon hydrogen is the classic example of why that simplification doesn't work. Carbon and hydrogen have a difference in electronegativity of 0.1. So it is a classic nonpolar bond, right? So this is really what we look at to decide if it's going to be polar or nonpolar. The only problem is you're not going to memorize those electronegativity values. They have to be given to you. All right, but technically this is how we decide. So as an example, if I, instead of bromine and fluorine, if I had made a bond between bromine and chlorine, what I can see here is the difference now is only 0.2. So that should be nonpolar because the difference here is so small that essentially they're sharing it evenly. If it's between chlorine and fluorine, difference here would be 1, then that should be polar. The other one we were asked to do here is the hydrogen chloride, HCl. So the only thing you want to remember here is hydrogen only has the 1 electron to come in with. So again, it follows the duet rule rather than the octet rule. And the chlorine comes in with 7. And so then if I look at the overlap, right, showing that orbital overlap, then hydrogen and chlorine each share 1 of their electrons. Chlorine has now satisfied the octet rule, hydrogen the duet rule. That difference in electronegativity between hydrogen and chlorine is 0.9, right? 3 minus 2.1, so we get a 0.9. And so again, this is going to be polar. Chlorine is much more electronegative, right? Remember from our trend from last semester, last chapter, electronegativity, fluorine is our most electronegative element. Chlorine is right below it. So imagine your tug of war, pretty strong pull towards the chlorine, not quite a strong pull towards the hydrogen. So we're going to have a negative end and a positive end. And again, that's where the term polar, right? Because we've got poles like poles on a magnet. Now, each of those structures that we looked at, they were simple 2-atom molecules. So pretty easy. We didn't have to worry about, okay, what's the center element supposed to be, or how many bonds will it be? I mean, we had to do that a little bit up here with nitrogen and oxygen, but because these were diatomics, if oxygen wants 2, the other oxygen wants 2, right? So that these were somewhat simple. What we're going to look at next are not going to be as simple. So what I have here for you, this has always been my way of doing Lewis structures, and a lot of books don't do this. They instead, and Dr. Musgrave kind of knows this too, you start with your Lewis structure for each of the atoms by themselves. And then when you put the atoms together, you kind of just move stuff around until you make the octet. I actually really like going through this. It takes a little more time up front, but it'll tell you exactly how many bonds you need. Like, will single bonds work, double bonds? It'll tell you if you're going to end up with an expanded octet. There's a lot of, I don't know, I like this. I like doing this. So this is how I do it. All right. So first thing is, I'm going to start with what I think is a pretty simple molecule. We're just going to do CH4. All right, methane. Now, the first job I have is to make what's called a skeletal structure, which just means, okay, we're kind of thinking again about Lewis structures. We have our element and we have 4 bonding sites, right? Now, when we were looking at them as just atoms, we did the dots, right? Top, bottom, left, and right. But now if we look at them as bonding, we have these 4 bonding areas, right? Top, bottom, left, and right. So there should be a center element and then up to 4 bonding sites. So when we look at the skeletal structure, basically that's what we're doing. We're saying, okay, this should be the center. And then the rest of these should be on the outside. That's what we start with. So the rule with the center element is number one, the center element has to be less electronegative. And that means the center element is the one that's farther away from fluorine on the periodic table, right? Because if fluorine is the most electronegative, the element farthest away from it should be the least electronegative. So that's number one. The exception to this, however, right, is that hydrogen, because it follows a duet rule, it can't have anything more than one bond. Once it takes the one bond, that's the 1s2, that's the duet rule, right? So hydrogen, right, can never be in the middle. So if I look at just what we talked about with number one, if I'm going to make a skeletal structure here, I'm going to put carbon in the middle, and then I'm going to put hydrogen on up to 4 bonding sites. And step 2 says, let's start looking at the electrons. Now, what I've done here so far is I have connected each of those hydrogens to the center carbon using a bonding pair of electrons. So when you write a bond, feel free to just write it as a dash like I've done here. When I was doing this as a student, I always like to emphasize the dots. You don't have to do that. But when I was learning this, it just kind of helped me visualize, okay, each bond is two valence electrons. So anyway, at this point, I have a center carbon. There's a total of 4 single bonds. Each hydrogen is attached to the center carbon with a single bond. Now, the terminal elements on the end, they don't bond together. Technically they do, but that doesn't come till organic. We won't worry about that now. So what we're going to always look at is the terminal attaching to the center, and that's it. So the next thing that we have to satisfy is the valence electrons are the important ones because they engage in the bonding. They decide what happens, right? Like we saw, oxygen had to be a double bond. We're not borrowing core, we're just taking valence electrons. So what we have to do is say, okay, well, how many valence electrons do we have for this compound? And that number of electrons, that should be in my picture, in my Lewis structure. So when I look at carbon on the periodic table, this is why I mentioned earlier, we need the quick graph, right? Carbon has 4 valence electrons, not the total of 6 electrons, the atomic number, but 4 valence. 2 are core, right, the helium core, and then the S2P2 valence, so a total of 4 valence electrons. So carbon comes in with 4 valence electrons. Each hydrogen comes in with 1 valence electron. But since there are 4 hydrogens here, I need to multiply that by 4. So 4 plus 1 plus 1 plus 1 plus 1 means I have a total of 8 valence electrons. Now then, that's step 2, right? Sum all of your valence electrons, looking at that group number from the periodic table. All right, and then we've used a single bond to connect every terminal element to the center element. And then step 4 on the next page is, okay, if we only have 8 valence electrons, how many have we used in those 4 initial bonds? So you want to subtract 2 electrons for each bond. So we used 2, 4, 6, 8 electrons already. So to start with, we had 8 valence electrons. We used 8 electrons in those 4 single bonds, right? Each bond represents 2. So that means we don't have any electrons left over. There's nothing left. So that doesn't always happen, right? This is a simple molecule that we're starting with. Now what I'm going to do is I'm going to go draw my circles, right? Hydrogen looks happy. Looks like it's 1s2. Duet rule is satisfied. So each of those 4 hydrogens looks good. Now let's look at the carbon. So drawing that overlap, right? Now when I look at carbon in its space, 2, 4, 6, 8, right? So the octet rule is satisfied. Carbon came in with 4. Each hydrogen brought in additional 1. So 2, 4, 6, 8, carbon has the octet rule satisfied. So this is the structure for methane. We only had to have single bonds, nothing weird, no extra electrons, no too little. That won't always be the case though, but that's how we begin this. All right, so we subtracted 2 electrons for each bond, and sometimes you'll have some left over, right? And so that'll be on our next example. All right, so next page, we'll get to 4 and 5 here with the next example. All All right, first one here, we have methanol and we have carbon monoxide and carbon dioxide. So the first thing is the carbon monoxide and carbon dioxide. I'm actually going to start with those two, right? They're simpler. The methanol maybe doesn't look quite as simple because it has more than 5, right? So if we're thinking about a center element with 4 bonding sites, there should only be 1 element, 2, 3, 4, and 5. And this one has 6. So that might be confusing to start. So let me do carbon monoxide first. All right, so carbon monoxide, I don't have to worry about a center element. So that's nice. We can put it however we want. You can do oxygen, then carbon, or carbon, then oxygen. Doesn't matter because molecules flip anyway, right? So we're going to just attach the carbon and the oxygen with a single bond, right? Just holding them together. That's it. That's all we do so far. Skeletal structure done. Now I'm going to go and count my valence electrons. Carbon, like we saw, comes in with 4. Oxygen comes in with 6. So I have 10 valence electrons. Now I put a little star next to that because that is my number, no more, no less. I can't use any more than 10 because I don't have that. I only have 10 valence electrons. I can't use any less because I can't have some left over. We have to make those 10 electrons work in such a way that everybody gets to an octet feeling. All right, so now, first thing is, how many did we use? We used 2 electrons in that one single bond. So we have 8 electrons left over. Right now, if I draw my circles, the oxygen in its circle only has 2 electrons. So it would need 6 more to get to 8, right? It only has 2. So it needs 2, 4, 6, right? It needs 8 more to get to the octet rule. The carbon, same boat, right? It has 2, needs 6 more. So if I add those two together, 6 plus 6 is 12. So 12 electrons would be needed to complete the octet. So what that tells me right there is that carbon monoxide is not held together by a single bond. There's no way for that to work. I don't have enough electrons left over to go through and make the octet happy for carbon and oxygen. So how do I do this? So again, the analogy, my brain likes to make a lot of analogies. I think of like 12 kids and 8 toys, right? What do you tell them to do? They have to share. So you have to make the carbon and oxygen share more. And the reason why I like the math is the question is, okay, well, how much more? And the math tells you there's a difference here of 4 electrons. You are 4 electrons short. And that means we need 2 more bonds. All right, remember, each bond is 2 electrons. So if I'm 4 electrons short, instead of just 1 more bond, I need 2 more bonds. So take your number of electrons that you are short, divide it by 2, and that tells you how many more bonds you would need. So this is additional bonds, not just a single bond and then make it a double. We need to take a single bond and make it a triple. So what we're going to have here at the end is we're going to have the carbon. Instead of 1 bond, we need to add 2 more, so a triple bond to the oxygen. And then if I think about my circles here, the oxygen and the carbon, they both are feeling 2, 4, 6 electrons in their circle. So the oxygen needs 2 more and the carbon needs 2 more. And so that should be my final structure for the carbon monoxide. So one thing I always like to do at the end is I go back to my valence and make sure that that's what I've got here. Because again, that's my number for carbon monoxide, no more, no less. So 2, 4, 6, 8, 10 electrons are there. So that's rule number 1, valence electrons satisfied, no more, no less. The other thing is the octet rule. So oxygen in its circle, 2, 4, 6, 8, carbon, 2, 4, 6, 8. So both have the octet satisfied. I only use 10 valence electrons. So question would be, what type of bond holds together carbon monoxide? And you would say triple bond. We have to have a triple bond to make it work. All right, so that's carbon monoxide. Question?
Yeah.
Okay.
I thought carbon only had 4. Like we had a triple bond, but we added 2 more dots on the other side, making it a 5 valence electron.
So it does come in with 4, but it needs 4 more to finish out the octet. So it does look a little strange because then you're thinking, well, wait, oxygen brought in 5 and it's borrowing 3. and that's where formal charges will come in. But the carbon monoxide, yes, carbon comes in with 4, but it always wants to get to 8. So typically carbon will like to take 4 bonds like it did with the methane, the CH4. But just because of how the carbon and oxygen can come together, and this is the only way to make it work, they have to do a triple bond to get both of them to 8. So even though you look at this and you think, well, wait, are all 5 of these due to carbon? Technically, no. Carbon only brings in 4, oxygen brings in 6. So one of these bonds with 2 electrons in it, those both came from the oxygen. All right, so that's carbon monoxide. Now let's look at carbon dioxide. So for carbon dioxide, the skeletal structure here, the carbon will be in the center. It's farther away from the fluorine. So I'll put oxygen on one side, and then carbon in the middle, and then oxygen on the other side. And if you wanted to draw this like going up and down, that's also fine. That part doesn't matter. All right, so first thing is valence electrons. All right, so carbon comes in with 4. Oxygen each comes in with 6, group 6. But since there's 2 oxygens, I multiply that by 2. So 12 from the 2 oxygens plus 4 from the carbon means I have a total of 16 valence electrons. All right, now, how many have I used in those 2 initial bonds? I've used 4. All right, so 2 are here, 2 are here, so I used 4. So I have 12 electrons left over. All right, and now I go and look at my circles and figure out what I need to do. So both of the oxygens so far just have a single bond. So they have the 2 electrons in the circle. They would each need 6 more. And then the carbon in the center has 2, 4, right? So 4 electrons to get to 8, it would need 4 more. So if I take 6 plus 4 plus 6, I get 16. All right, so I would need 16 more to finish out the octet on every element there, the carbon and the 2 oxygens. Same problem I had before. I don't have enough electrons to make this work. I'm short by 4 electrons again. So we're gonna need 2 more bonds. Now, with the carbon monoxide, we only had one place to put it, right? We knew it had to go in the center. There was no other place to put it. So the single became a triple. In this case, do I make a triple and a single, or do I make 2 doubles? So formal charges would help us, but we haven't learned those just yet. So instead, what we're going to do is fall back on symmetry. Most of the time, symmetry is your friend when it comes to putting together molecular structure. So the carbon is going to be in the center, and we're going to put 1 additional bond on the left and 1 additional bond on the right. So carbon double bonded to the oxygen on the right, double bonded to the oxygen on the left. And like I said, if you don't put the dots in, you just want to do the dashes, that's fine. All right, so if I look at carbon right now, in its circle around it, carbon has 2, 4, 6, 8. So carbon is already full. All right, now what about the oxygen on the right? 2, 4 needs two more lone pairs, and the oxygen on the left, same thing, 2 more lone pairs. So now when I look at both of these oxygens, they both have their octet rule, 2, 4, 6, 8, 2, 4, 6, 8. So everybody has an octet rule. Remember, the last thing you always want to double check, because this is super important, is the number of valence electrons, right? The total. We had 16 to work with. 2, 4, 6, 8, 10, 12, 14, 16. There's my 16. Now, the only thing that kind of comes up here, oh, I just threw my pen across there. The only thing that comes up here is a lot of times when we talk about the orbital diagram, we say, oh, electrons prefer to sit separate. And now all of a sudden we're making sure that they're paired. So why is that? Why do we draw 2 lone pairs on the oxygen rather than a pair and 2 singles? And the reason for that is it's going back to wanting that noble gas S2P6. So everything should always end up in pairs. That is what's more stable here. So everything when it comes to a Lewis dot structure should be in pairs, either a bonding pair or what's called a lone pair, just a lone on the element. So in this carbon dioxide, we have 1, 2, 3, 4 bonding pairs. and 1, 2, 3, 4 lone pairs. All right, so that'll be my final structure for the carbon dioxide, is 2 double bonds for the CO2. All right, then the last structure that we've got here is the methanol, the CH3OH, and I think I might be able to fit that there. All right, so the CH3OH, the way that this is written here, if you looked at it, you might ask a couple of questions like, number one, why isn't the hydrogen in front? Okay, that's because it's not an acid. If it's an acid, the hydrogen is in front. If it's not in front, it's not an acid. That's number one. Number two, in organic, those rules change a little bit, by the way. Number two is this is a structural formula. And so what this helps me understand, and you'll see more of this when you go into organic, is that I've got a carbon center, and then it's H3, which means hydrogen on 3 of the sides. And then it says OH, which means the oxygen is attached to the carbon and the hydrogen is attached to the oxygen, right? The structural formula is showing the OH popping up this way as OH. So it's called an alcohol. So that's your alcohol group. So that's methanol, right? OL, anything that ends in OL is an alcohol. And it has that OH group, not to be confused with hydroxide, which is something we only see in ionic compounds when it's combined with a metal. With covalent compounds, it's an alcohol. But anyway, so this is our skeletal structure for the methanol. And for now, until you get into organic, this is how it has to be written for you to understand what the structure will look like. So carbon is almost always your center. Can't be the hydrogen. We know that because hydrogen can't ever be in the middle. And if it had to come down between carbon and oxygen, remember the less electronegative goes in the middle. So carbon on the middle, and then the hydrogen has to be on the end. We're just going to put an oxygen between the carbon and the hydrogen. All right, now when I go and look at my valence electrons, carbon comes in with 4. Each hydrogen comes in with 1. There are 1, 2, 3, 4 hydrogens here. So I got to multiply that by 4. And then oxygen comes in with 6. So I have a total of 14 electrons here. All right, and again, that's all my valence electrons. That's my number that I have to use, no more, no less. All right, so how many do I have so far? I've used 2, 4, 6, 8, and then 10. I've got 10 electrons that I've used. There's 4 electrons left over. Where do they go? All right, well, if I look at each of the hydrogens are good, right? They follow the duet rule. They each have 2, so hydrogen is done. If I look at carbon, 2, 4, 6, 8, carbon is also done. So oxygen hopefully is the one that needs 4 more electrons. And when I look at oxygen in the circle, 2, 4, so it needs 4 more. So there's where the other 4 electrons are going to go. And we weren't short electrons, so we didn't have to increase bonding or anything like that, like we did with carbon dioxide and carbon monoxide. We're just going to put those 2 lone pairs on the oxygen. So 14 electrons should be here. 2, 4, 6, 8, 10, 12, 14. There's my 14. So that would be the Lewis structure for the methanol. All right, I'm going to finish out the page and then we're going to take a break. The last thing we have to talk about here is, what if you have a polyatomic ion with a charge? What does that do to the electron count? So again, how is carbon monoxide stable? Carbon dioxide is stable and carbonate is stable, right? So it helps us understand this. So for carbonate, I'm going to do that one first. Same thing. We expect carbon should be the center element because it's less electronegative. Oxygen on any 3 sides held together with a single bond for now. And then I'm going to go and look at my valence electrons. All right, so carbon comes in with 4. Each oxygen comes in with 6. But since there are 3 oxygens, I got to multiply that by 3. And then the -2, because there's a charge on here, I have to think about what that does to my electron count. -2 means there's 2 extra negative particles here. So I have 2 extra electrons here. So 18 plus 2 plus 4, I have 24 total valence electrons. All right, and again, that's my number, no more, no less. I have to use 24. I've used 6 in these initial bonds, in the 3 bonds that I have so far. So I have 18 that are left over. right, now I draw my circles. You don't have to draw the circles, by the way. I just like it. It's visual. It's very visual for me. All right, so if I start with each of the oxygens, they all look the same. Each oxygen has 2 electrons in the circle. So each one of these would need 6 more. All right, and then I have to look at the carbon. Carbon has 6, so it needs 2 more. So if I add that all up, 6, 2, 6, and 6, that's 20. All right, so when I went through my math here, I saw that between the carbon, the 3 oxygens, and the extra 2 electrons in the polyatomic ion, I had 24 electrons to work with. Again, no more, no less. I have to use 24. I have to do it in such a way that everybody ends up with an octet. I already used 6 in those 3 initial bonds, which means I have 18 left to place, but I need 20 to go through and make everybody happy with an octet. So like we saw with the carbon monoxide and the carbon dioxide, that means we are 2 electrons short. So I need 1 more bond. Now, it doesn't matter where you put the double bond, because that's going to segue into something called resonance, which we're going to talk about in a little bit. So you can put the bond, the extra bond on the left, on the bottom, on the right, does not matter. I'm going to put it on the left. So oxygen on the left will have the double bond. On the right will stay a single, and on the bottom will stay a single. Now, if I look at my carbon, 2, 4, 6, 8, carbon is done. The oxygens with the single bond would need 3 lone pairs to finish off the octet. And then the oxygen with the double bond would need 4 lone pairs to finish off the octet. All right, so again, I want to make sure and go back and make sure 24 electrons are here, no more, no less, right? So I've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So there's my 24. And then just make sure everybody has an octet. So oxygen, 2, 4, 6, 8. Oxygen on the bottom, 2, 4, 6, 8. Carbon, 2, 4, 6, 8. And then oxygen with the double bond, 2, 4, 6, 8. With polyatomic ions, whoever made the rules, they said, okay, let's put it in brackets. Sorry, I didn't mean to cut off the lone pair there. And then outside brackets, put in the charge. So just to say, yes, there are 2 extra electrons here. All right, so this would be the final answer for the carbonate. All right, the carbonate is held together by 1 double bond and 2 single bonds. Now hydronium, much easier. We have H3O plus. And so for this one, we know oxygen has to be the center because hydrogen can't be. And then we'll put hydrogen on 3 sides. All right, when I go and count my valence electrons, oxygen comes in with 6. Each hydrogen comes in with 1. And now in this case, we have a charge of +1, which means we've lost an electron. So we have 8 electrons here total to work with. We've used 6 in these 3 initial bonds. So if I take out the 6, I've got 2 left. And those 2 should go right there on the oxygen to finish off the octet. And that's my structure for hydronium. All right, so that's all done, nice and easy. Overall, sorry, the charge here, I'll put it up here, it's a +1. But the hydrogen has followed the duet rule, oxygen 2, 4, 6, 8. And we only used 8 electrons because that's all we had for the hydronium. So if you have an ion, if it's a negative charge, right, you add that to your electron count. If it's a positive charge, you subtract, right? So that's a good place for me to stop. It's almost 12, it is 12:20, sorry. So let me pause here, come back at 12:25. All right, so picking up where we left off, we had the Lewis structure for carbonate and hydronium, and then we had done, methanol, carbon dioxide, and carbon monoxide. And I had mentioned the term resonance before. So here's the definition on the next page. Resonance, right, is when two or more of the Lewis structures have the same skeletal formula. That's the key. So same center element, same terminal elements, but you could arrange the electrons differently. And basically the simple answer is the double bond can move. So remember when we were doing carbonate, we had ended up saying, okay, well, one of these is going to be the double bond. And I said, it doesn't matter where you put it. You can put it on the left, on the right, or on the bottom. That's resonance. If I draw the double bond on the left, or if I draw a different structure with it on the right, or a different structure where it's on the bottom, that's resonance. That's what resonance is. The center element is the same, the terminal elements are the same. The only thing that's changing is where we put that double bond. That's the only structure here where resonance was possible. Carbon monoxide can't change it. Carbon dioxide can't change that double, right? Methanol didn't have any double bonds anyway. So it's only when you have a double bond, but you could draw it in a different position and still have the same structure. So it may not seem like it's that important, right? Like, why would that, because like we said, molecules can move and flip anyway. So what difference does it make if I draw it on the left or the right? And where this comes in is we're going to look at bond energies in just a little bit, where the double bond has a certain bond energy versus a single bond. And what ends up happening when you have a resonance hybrid, so you have a molecule where all of those, basically the double bond can move, it can resonate between the molecule. The bond energy isn't quite a double bond and it's not a single bond, it's somewhere in the middle. And so they noticed that, and then they came up with this idea with resonance. All right, and so that's what this says, a resonance hybrid. So a hybrid of, in this case, 3 possible structures for carbonate, 1, 2, or 3, depending on where you put the double bond. That hybrid develops, and it actually stabilizes the ion, and that leads to stronger acids, by the way, but we don't need to worry about that. And it explained the anomalies that they were seeing with bond energies. So carbonate didn't have like a strict single double bond type bond energy. It had somewhere in the middle, like a hybrid. All right, so which of the structures do we do? The one that would have the resonance, that would be the carbonate. All right, and so again, based on the structure that we drew, we had it as oxygen with the double bond on the left. All right, single bond on the right. Oh, and that's not really gonna fit, sorry. Single bond on the bottom. All right, and then the resonance, we could show instead the single bond on the left and the double bond on the right. Right, and then another possibility there would be that you could draw the double bond on the bottom, right? All right, kind of messy. Sorry, I should definitely left myself some more space. But you understand that the skeletal structure stays the same, right? We have a carbon center with 3 attached oxygens. We can't swap one of these out for sulfur, right? Then we've changed the skeletal structure. And the only thing that we're swapping is where we put the double bond, right? Do we put it on the left, the right, or the bottom? And that's the hybrid. That's the resonance hybrid. Okay, so that's resonance. Formal charge, this is new. We didn't talk about this in the intro. A formal charge is going to help us understand sometimes that this actually kind of goes back to Adam's question, what he noticed about, well, how is carbon only bringing in 4 electrons, but now it looks like it has 5. The formal charges here are going to help us try to get the very best structure we can for whatever the Lewis structure is that we're looking for. And it is also going to show us that there are times when we need to, what it was called, expand the octet. So in intro, we never talked about that. We just said, nope, octet rule, duet rule for hydrogen, period. End of sentence. We don't talk about it. But what happens is we're creating orbital hybrids, right? And we'll see this in the next chapter when we do geometries, that the spherical s orbit and the p axis, right, space, they hybridize into different geometries. And that's why you can create, 4 bonds around the carbon. Because if you're thinking, well, how do you do an S overlap with a PX, PY, PZ, right? So they hybridize together and they make what's called a tetrahedral shape. But it turns out that some elements can not only hybridize their S and P orbitals, but they can hybridize their D orbitals as well. Now, if you think about oxygen, oxygen does not have that option. It's in row 2. And like we learned in row 2, energy shell 2, there's only a 2s and a 2p. There's no 2d. But when I get to row 3, like with phosphorus, phosphorus 3 has a 3s2, 3p3. but there are 3 d orbitals in that third energy shell. So phosphorus could expand its octet if it had to and hybridize with those d orbitals, because there are d orbitals to be had in the third shell. The same is true with arsenic. Right now it has the 4s2, 4p6, and then 4d10 possibility, right? So when it's talking about expanding the octet, it is only possible with elements that are in row 3 or larger, right? Or, lower on the periodic table, right? It does not work with anything in rows 1 or 2 because there's no d orbitals to hybridize with in energy shell 1, energy shell 2. So when it talks about expanding the octet, not possible for nitrogen, oxygen, fluorine, right? Only possible for the others. The elements, the nonmetals lower than that in the P block. Now, formal charges are going to help us sort of start to see this. So the formal charge, it's a fictitious charge. It's not like it's an ionic charge. It's not even like it's an oxidation state. This is only to help us with Lewis structures. And it helps us get the correct Lewis structure. When it looks like more than one is possible, Lewis structures will help us figure it out. What you do to assign formal charges is you first look at the element, like let's say oxygen. You start with the number of valence electrons for that element. So oxygen has 6. You subtract 1 electron per bonding pair. So in other words, these 2 electrons we're going to assign to the oxygen. The other 2 we're assigning to the carbon for formal charges. So we take away, the oxygen comes in with 6 electrons. It has 1, 2 for the 2 bonds. And then each of those lone electrons are just solely for the oxygen. So basically what we do is we look at the structure and we look at each element and we assign each element its own set of electrons. So when I look at the formal charges, oxygen comes in with 6 and I've assigned it 1, 2, 3, 4, 5, and 6. Carbon comes in with 4 and I've assigned it 1, 2, 3, 4. Oxygen with the right on the single bond comes in with 6 and I've assigned it 1, 2, 3, 4. Oops, and I forgot 5, 6, and then 7, right? So then you're like, well, wait a minute, that's not quite right, because oxygen comes in with 6 and now it looks like it has 7. So 6 minus 7 would be a -1. But because something here is carrying a negative charge, because it's a negative polyatomic ion, it's okay that the formal charge doesn't all go to 0. So the goal is to get formal charges to 0. But if you have a polyatomic ion that overall has a charge, it's not possible, right? But otherwise, we want our charges to go to 0. So we want to keep formal charges as small as possible. 0 is best. And adjacent elements, right, side by side, shouldn't be positive and negative. All right, when that happens, that's when it starts to look like we're going to expand the octet. All right, so we're going to do Lewis structures for the cyanate and try to figure out which one would be the correct structure. So let's start with carbon in the center. That part we know because it's the least electronegative. Oxygen on one side, nitrogen on the other. Then if I go and look at my valence electrons, oxygen comes in with 6, carbon comes in with 4, nitrogen comes in with 5, and because it's a -1 polyatomic ion, there's an extra electron here. So I have 6 plus 4 is 10, plus another 16. I have a total of 16 valence electrons. I've used 4 in those 2 bonds. So I have 12 electrons left. All right, so I'm just adding, right, the valence electrons, again, that's just coming right from the group number. Just want to make sure that that's clear. So oxygen is 6, carbon is 4, nitrogen 5. So the charge -1 means there's an extra electron here. So I've got 16 total to work with. I've used 4 in those 2 initial bonds. So 16 minus 4, I've got 12 electrons left. Now, if I go and look at my circles and see how much more everybody needs. All right, the oxygen has a single bond, so it would need 6 more to complete the octet. Same for the nitrogen. And then carbon has 2 single bonds, so it would need 4 more to get to the octet. So 6, 4, and 6, that would be 16. Nope, sorry. Yes, sorry. Doing 2 things at once. Okay. So 12 electrons were left over. 16 are needed to complete the octet. As we saw before, this is 4 electrons short. So I need 2 more bonds.
I thought nitrogen only needed 5 more because you put up the valence electrons.
So remember here, the valence electrons and the octet rule are two different things. So nitrogen comes in with 5, but everybody always wants to have 8. So yeah, so the goal, and this is where formal charges and valence electrons, it all kind of gets a little weird. So when you're right, nitrogen comes in with 5, and we want a valence, like a formal charge of 0, which makes us think, okay, we only want to assign 5 electrons to nitrogen. But not to be confusing, everybody still wants the octet. So always the goal, except for hydrogen, is to somehow figure out, make this work where everybody has an octet. So both the oxygen and nitrogen have 2. They need 6 more to get to 8. Carbon has 4, needs 4 more to get to 8. So when we got through our count, our number of electrons, we saw, okay, 12 electrons left over. I need 16 to make everybody happy. I'm 4 electrons short, so I need to do 2 more bonds. So the carbon dioxide that we did earlier, that was a little bit easier because we had symmetry, right? So when we got to that same point, when we got here, it was like, okay, well, I need 2 more bonds. I'm not going to make a triple and a single because that's not symmetrical. It makes sense to make a double and a double. I don't have that here, right? But we're going to try it. It says draw the 3 possible Lewis structures, and then we're going to figure out which one is best. Okay, so the 3 possible structures. Structure number 1 is we're going to put a triple bond on the oxygen to the carbon and a single bond to the nitrogen, right? We wanted 2 more bonds. So we'll put those 2 right here for the oxygen and carbon. To finish out the octet on the oxygen, I would need a lone pair. Carbon is now full, 2, 4, 6, 8, so that's done. Nitrogen would need 3 more lone pairs to get to 8. All right, so just making sure there should be 16 electrons here, 2, 4, 6, 8, 10, 12, 14, wait a minute, 2, 6, 8, 10, 12, 14, 16, there we go. Now the circles, again, if they're not helpful, don't worry about it, but oxygen, right, has 8, the octet rule is satisfied. The carbon has 8, 2, 4, 6, 8, octet rule satisfied, and nitrogen also has 8. So that's one possible structure. Then let's try it where they're both double bonds. So oxygen double bonded to carbon, double bonded to nitrogen. So right, we're going back to where we began, but we said we needed 2 more bonds. Okay, so let's try it where now we just put 1 on each. The oxygen on the left needs 2 lone pairs. The nitrogen on the right needs 2 lone pairs. So that's another possible structure. Again, there should be 16 electrons here. 2, 4, 6, 8, 10, 12, 14, 16. And everybody should have an octet. Oxygen, 2, 4, 6, 8. Carbon has 8. Nitrogen has 8. So that's another possible structure, right? Everybody has the octet rule. I've used my magic number of electrons here, which is 16, right? So that is another possible structure. The last possibility is let's have oxygen keep the single bond, and then we'll put the triple bond on the side with the nitrogen. And if I do that, nitrogen now only needs a lone pair to finish out the octet. The oxygen needed 3. So again, if I look at my circles, oxygen has 8, 2, 4, 6, 8. Carbon has 8, and nitrogen has 8. So everybody has the octet rule. 2, 4, 6, 8, 10, 12, 14, 16. There's my 16 electrons. So all 3 of those would be possible. So this is where formal charges will help us, right? It'll
Excuse
help
me.
us. Yeah, go ahead, Alex.
Sorry. I just keep on getting confused because I see that we have a -1 charge. So we're able to add 1 more valence electron, but on number 1, you added 2 on the nitrogen.
So the 1 extra electron comes in here in the beginning. So when we took our number of valence electrons that we come in with, oxygen brings in 6, carbon 4, nitrogen 5. And then because of the charge, that -1, we go ahead and add it in here. So I know I have 16 electrons to work with. Now,
Right.
when we draw the 3 structures here, we're not saying which of those electrons is the extra electron. But what we're saying is there should be 16 here total. Does that make sense? So like when I draw this first structure, I'm not saying that, this 1 electron is extra. Is that what does that help?
I was just like, sorry, I'm still confused. The nitrogen has 5, but it has 7 in the end.
Right. So actually that's what formal charges are going to tell us. So you're thinking ahead. So at this point, what we've got is the octet, right? That's what we've done so far with Lewis structures is, okay, let's take these electrons and let's distribute them in such a way that everybody has an octet. And so that's what we did, right? We've got 2, 4, 6, 8 for the oxygen, nitrogen 2, 4, 6, 8. That seems fine, right? The carbon 2, 4, 6, 8. So everybody has the octet. The formal charges, though, are going to tell us, which is what you're noticing, that that's not the right structure. All right, but we use this, or not we, but it's a great example to use because there are 3 possible compounds. Everything we've learned with Lewis structures so far is, okay, make your valence electron count work, right? So that everybody has an octet. And if you're short electrons, you can create double or triple bonds as needed. But at this point, the only thing we're really focusing on is getting your number of electrons, your total, and making sure they're distributed in such a way that everybody has an octet. That's it. That's all we've done. And all 3 of these answers satisfy that. Everybody has an octet. We've used 16 electrons in each of those structures. So at this point, all 3 of those structures are correct. What we're now getting into, which we didn't cover in intro chem, is, okay, that's nice that there's 3 possible structures, but there really should only be 1, right? So which one of those is the right one? And I think this is why it's confusing, because this is what formal charges will help us do. So when I do a formal charge, I'm going to look at each of those elements. So I'm going to draw like a little table. So my formal charges, I'm going to look at oxygen, carbon, and nitrogen. So for each of those, let's look at the formal charges. All right, so in structure number 1, this first structure, all right, so I'll label it number 1. Oxygen comes in with 6, right? That's always true. Carbon comes in with 4, nitrogen comes in with 5. So that's always what you do, is you start with your number of valence electrons, which is the group number, which is the same thing we used over here. The oxygen in this first structure, we've assigned it, right? 1 per bonding pair. So basically what we're saying is 1, 2, 3, those 3 we are assigning to the oxygen, and then 4 and 5, right? So I think this is where it gets confusing. You're like, well, wait, I've only assigned it 5. So overall, that doesn't seem right. It should have 6. And the formal charge is showing you that's probably not right. It has a net +1. So oxygen comes in with 6. We've only assigned it 5. 6 minus 5 is a +1. Now the carbon, I'm just going to do in red. Carbon, it comes in with 4, and we've assigned it 1, 2, 3, and 4. So 4 minus 4 goes to 0. So carbon looks okay, right? Now let's look at nitrogen. Nitrogen comes in with 5, and now I'm going to use my purple pen. We've assigned it 1, 2, 3, 4, 5, 6, and then 7. So 5 minus 7 means a -2. So if I add up all my formal charges, +1, 0, -2, I get a net -1, which matches the charge on the polyatomic ion, right? So I know I'm not going to get all my formal charges to 0 for the thiocyanate, or for the cyanate. There should be a net formal charge of -1, because that's the charge on the polyatomic ion. And that's what I've got here, but I really want my formal charges to go to 0. So this structure doesn't look right. And you kind of felt that, right? You were like, ugh, nitrogen doesn't look right. It only has 5 electrons, and now I've loaded it with electrons. So now let's look at the second structure, right? So now if I go to my second structure, let's start with oxygen, comes in with 6. And now I've assigned it 1, 2, 3, 4, 5, and 6. So 6 minus 6, that goes to 0. That seems good. Carbon comes in with 4. And how many have I assigned it? Carbon, 1, 2, 3, and 4. So half of each bond, right? So 4 minus 4 goes to 0. So that also looks good, right? So we always want charges to go to 0 if we can. Now with the nitrogen, we come in with 5, group number 5. And now I've assigned it 1, 2, 3, 4, 5, and 6. So 5 minus 6, I get a -1. And that definitely seems better, right? We got more formal charges to 0. We have a net -1, which is what we should get anyway, because that's the charge on the polyatomic. But here's why this is not the right structure yet. The reason why is if you have a net negative charge, like if something has to carry a negative charge because it's a polyatomic and you know something here has to be -1, that minus should always go to the more electronegative element. That makes sense, right? The element that is most in desire of the electron density should be the one that carries that negative charge. So when I look at my periodic table, right, fluorine is our most electronegative element, oxygen is the second most. So that -1 formal charge, it shouldn't go to nitrogen, it should go to the oxygen. So let's check our last structure here and see if this one's better. All right, so we got one more structure to go. For the third structure, oxygen again comes in with 6, and now we've assigned it 1, 2, 3, 4, 5, 6, and 7. So 6 minus 7 means -1 overall. Then with the carbon comes in with 4, and we've assigned it 1, 2, 3, and 4. So carbon goes to 0, so that's good. And then my last one here, the nitrogen comes in with 5, and we've assigned it 1, 2, 3, 4, and 5. So it's also gone to 0. So the second and third structure, they kind of look like a wash, right? You got 2 with a formal charge of 0, 1 with -1. Again, you can't get them all to 0 because something here has to carry a -1. The third structure, same thing, 2 are at a 0, 1 carries a -1. So which one is right? So the formal charges are just a way for us to look at what are possible structures and figure out which one is the right one. And what I look at here is, again, what I talked about, the more electronegative element. All right, so the more electronegative En element carries the -1 formal charge. And so in this case, it's going to be the oxygen, right? Oxygen is more electronegative. So that tells me then that the right structure for this cyanate polyatomic ion is the third and final one that we did. That is the better structure. And I think this goes back to the question that Adam had, like this one looks, it just looks like it seems right. like nitrogen came in with 5 and it borrowed 3. That makes sense. Oxygen comes in with 6, but it, then it borrows a couple. So this last structure, the third one that we drew, had the best formal charges in that 2 were 0, 1 was -1, which again, you can't get rid of because something here has to carry the -1. But the -1 was carried by the more electronegative element. So that would be the best of the 3 possible structures for cyanate. Now, this is not the same as resonance, right? Because sometimes they get confused, especially because we teach them back to back. And you think, okay, well, the bond is just moving, right? So isn't that resonance? And the answer is no. When you have resonance, let me go back up here. The formal charges are all the same. Like one of the oxygens here carries a formal charge of 0, and the other 2 are -1. So net, nothing has changed. It's not like the less electronegative element should have the 0 formal charge, right? That's like what we had here. We had 3 different elements, different formal charges. This is not resonance, right? So resonance is really when you have the same structure, we're just moving the double bond, right? And it kind of almost seems silly to think about, but it helps us understand the bond energies. So this right here, what we drew for the cyanate, this is not resonance. That's not what we look at for resonance. All right, but this was a good way to explain why formal charges can help us understand the correct structure. All 3 of them satisfied the octet rule. All 3 of them had a total of 16 electrons present, but using the formal charges, we can figure out that the third structure is the best one. All right. Now, we talked a lot about everything being paired, everything being the octet rule. Again, always exceptions, right? You can have what are called free radicals. You kind of hear about those. Free radicals are highly unstable compounds, and they have a total valence electron count that is an odd number. And so what'll end up happening is like nitrogen, just as an example, instead of this being a lone pair, it would just have a single electron there. And that's highly unstable, right? These are very reactive molecules. So I don't typically give them. But in case you're wondering, because we have heard that terminology, free radicals, right? That's why they're free radicals, is they have an odd number of electrons, and then that creates that one of those electrons is not going to be as a pair, and that makes it very unhappy. Now, the boron right, is another exception to the octet rule. We talked about how hydrogen follows the duet rule. That made sense because there's only a 1s2. But boron is a little bit different. It's an exception, but you don't think it should be because there's s2p6, right? But for whatever reason, boron likes to take 3 bonds and then that's it. So it won't have 8 electrons around it. It'll only have 6. So just as, let me kind of draw this out. So you'll often see boron, like boron trihydride, BH3. And so the boron doesn't look like the octet has been satisfied. And that's okay, that's just boron. All right, so boron is one of the exceptions. All right, it only takes 6 electrons typically around it. All right. Now, the other exception that'll come up more often is when you can have an expanded octet. And that's what I talked about earlier. This is only possible when the s and p orbitals can hybridize with d orbitals. And those d orbitals have to be available in the same energy shell, the valence shell. So a row 2 element cannot expand the octet. So nitrogen, oxygen, fluorine, they can't do this. So,
Professor, if
yeah, go
I
ahead.
have a moment, before we keep going on, I'm confused by something. In something like the, I think we were just working with CO2. We had multiple different Lewis structures with multiple different pairings, like some had 2 and 2 or 1 and 3. How do you determine that? Because I assume that there's just a given correct one.
Right.
Oh, no, OCN. Sorry, cyanate. But how do you determine the correct one for that?
Yeah, so the formal charges are what you have to do to correct it. Because you're right, up until now, we haven't learned formal charges. And if I ignored that, they all look like they should be right? Because they all have satisfied the octet rule. They all have those 16 total electrons in it. So the formal charges is the new piece of the puzzle that says, okay, now that we know how to do Lewis structures, let's take this a step further. And when we got to this initial skeletal structure and we looked at our total valence electrons and we realized that we needed 2 additional bonds, then the question was, okay, well, where do I put them? Do I put them both on the left, both on the right, or 1 on each? So we had 3 possible structures. And the only way to know which one is the right one is to go through all of this with the formal charges. That's how you know which one is the right one.
So real quick, because I'm just wanting to make sure that I'm understanding this. The way that we work with the formal charges is we take the actual charge of each atom, and then when writing out the Lewis structure, each electron is its own quote unquote minus charge in this case.
I wouldn't think of it in terms of charge. What you want to do is start with your valence electron number, which is the group number, right? So oxygen starts out with 6, carbon 4, nitrogen 5. And then I remember when I was doing this as a student, I would draw, like in this molecule here, each bond, I would have it be like a dot and an X. And so then it would say, okay, the dots are assigned to the oxygen and the X's I assign to the carbon. And that's not right. It's not, it shouldn't be X's and dots. They're just dots, right? So I've gotten over that now. But I tried to color code them here because like oxygen brings 6 to the table, right? That's the number of electrons it brings into this structure. But the way that we drew this structure is we've only assigned oxygen 1, 2, 3, 4, 5. So 6 minus 5 means it has a net +1. That doesn't seem right. Then carbon, we know, brings in 4 because that's the valence electron count, the group number. And we are assigning it 1, 2, 3, 4, the ones I wrote in red. So there's those 4. So that went to 0. That looks pretty good. Nitrogen comes in with 5, group 5, but we've assigned it 1, 2, 3, 4, 5, 6, 7 in purple. So when we do the formal charges, we start with, okay, how many are they supposed to have? That's the group number. And how many in this structure, how many did we give them?
So wait, how did with the nitrogen, how did we manage to go from it has 5 valence electrons to all of a sudden we've got 7 electrons orbiting it?
Right. So I mean, no, you don't want to say 7 orbiting it because again, remember everybody wants 8. So you don't want to say it has 7, it has 8. Everybody wants 8. So each of these 3 has 8 in the circle, and that's what everybody's hoping for is that noble gas S2P6.
Okay, so each of the pairings, each of the connections is in reality worth two of the little blips, two of the little dots to charge.
Right, right. So like nitrogen in the circle has 2, 4, 6, 8. When we do a formal charge though, we say, well, let's put that one on the nitrogen side, and this one is really going to give credit to the carbon. So only in the case of the formal charges, we basically cut the bond and we say, okay, the one on the left goes, sorry, the one on the right goes to nitrogen, the one on the left goes to carbon. But total, they all have 8. They all have the octet rule. And that's what every element always wants, is the S2P6. Again, except for hydrogen and boron, and there's some others. But for the most part, that's always what the goal is, right? We want to make sure everybody gets 8 electrons. We want to use our total number of valence electrons, no more, no less. And now what we're adding to that is if we end up with possible different structures, which we won't always, right? Like methane, it's only going to be single bonds. Carbon monoxide was always going to just be one triple bond. But sometimes we get into this area where it's like, well, okay, I know I need 2 more bonds. Where do I put them? Do I put them on the left? Do I put them on the right? Do I put one on each? And that's when you draw your 3 structures and look at the formal charges to help you decide which is the right one. Does that make more sense?
That does, yes.
Okay, very good. Okay, so we talked about exceptions. We talked about hydrogen in the beginning, duet rule, and then we looked at boron, also sometimes being a problem. Honestly, I don't use boron very much, but if you see it in the homework, don't pull your hair out on that one. Boron likes 3 bonds and that's it. So the octet rule is never satisfied. So just don't worry about that one. It's kind of an anomaly. Now the expanded octet is going to show up more, right? So the other exception that we talked about was when the S and P orbitals hybridize and kind of morph together and they overlap in their geometries, which again is the next chapter, there are elements that can also hybridize with the d orbitals. And again, that's only going to be elements that have d orbitals, right, in their valence shell. That makes sense. So carbon, right, is in a 2 shell, NF2. And when you're in the second shell, you only have S and P, there's no D. So it can't hybridize into D. But if you have phosphorus, which is a 3S and a 3P, there is 3D there in that third shell. So it can expand the octet. All right, so that's what I talk about here, right? So expanded octet is possible. Doesn't mean it's always going to happen, but it is possible. And the only way we're going to know if it happens is through the formal charges. So the next question, it says, let's figure out the structure for sulfuric acid. Sulfuric acid is H2SO4. All right, if anybody is like slightly panicking and being like, wait a minute, I don't remember the nomenclature part of this, don't worry about it. I'll give you the structure. H2SO4 is the formula. Now, first thing is center element, right? Hydrogen, you can always ignore. It's never going to be in the center. So then it comes down to sulfur or oxygen, and oxygen is more electronegative. It's closer to fluorine, so that should not be in the center. So we're going to have sulfur in the center. Now, acids, the hydrogen always bonds to the oxygen. So the skeletal structure here is the sulfur would have 4 bonding oxygens around it, right? Like this would be sulfate if we were thinking about the polyatomic. And then on 2 of those hydrogens, we would have, or sorry, 2 of those oxygens, we would have hydrogen. So we have our sulfate polyatomic ion and then hydrogen attached to 2 of those oxygens. Now the valence electron count. All right, sulfur is group 6. Each oxygen is also 6, but since there's 4 of those, I have to multiply that by 4. And each hydrogen comes in with 1, but because there's 2 hydrogens here, I gotta multiply that by 2. So 6 times 4 is 24, plus 6 is 30, so I have a total of 32 valence electrons. So I have quite a bit here, right? And now I need to figure out where, how many have I used? Where should they all go? All right, so first, how many have I used? So each one of these bonds represents 2 electrons. So 2, 4, 6, 8, 10, and 12. So 1, 2, 3, 4, 5, 6 bonds. I've used 12 electrons. All right, so I've got 20 electrons left over. And then I'm going to see who needs what. All right, the hydrogens are good, right? Duet rule, as soon as hydrogen has a bond, hydrogen is good. The sulfur also looks good, right? 2, 4, 6, 8. So sulfur looks like that's done. The oxygens that are in the middle of hydrogen and sulfur, 2, 4, needs 4 more to get to 8. So again, we always want to target the 8. We want the octet rule. So both of those oxygens in the circle have 4, need 4 more. The oxygens with the single bond have 2 electrons. They would need 6 more. All right. So when I add up all of the electrons that would be needed, right? 6, 4, 6, 4, there's my 20. So that looks like it should be the correct structure then, right? Like we don't need double bonds because we talked about only needing double bonds when you're short electrons. So this looks like we have the right structure, right? So if I draw the new structure over here, I'd have hydrogen to the oxygen. The oxygen would have 2 lone pairs on it now to complete the octet, right? Then on the right side, same thing. And then the oxygen above and below would have 3 lone pairs to complete the octet. All right, so that looks like our structure. Let's just make sure 32 electrons here. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. So there's my 32 total electrons. Everybody has the octet except hydrogen. So now let's take a look at formal charges. All right, so I'm going to just put these in blue. All right, now hydrogen comes in with 1 valence electron, and we've assigned it 1 valence electron, right? We're saying that that one there is the hydrogen. And so formal charge on the hydrogen goes to 0. And the same would be true over here. This would be a 0. All right. Now the oxygens that are in the middle, right over these 2 here, they look the same. Oxygen comes in with 6, and we've assigned it 6, right? 1, 2, 3, 4, 5, and 6. All right, so again, formal charge there is 0. This oxygen looks the same. We've assigned it 6, so formal charge there is also 0. So far, formal charges are looking good. Yeah, go ahead.
The reason why we keep the 6 dots around the oxygens without the hydrogen is because S already has 6, so it makes up the bonds already, correct?
Yeah, but I think you're thinking ahead again, and you're seeing that that probably doesn't seem quite right. But you're right. But again, at this point, we're still focusing on the octet, right? So the oxygen here, it had to have 6 because it only had 2. So it has to complete the octet. So 2, 4, 6, 8. Same with here. We needed 3 lone pairs because we only had the 1 bonding pair. So we have a total of 8. So that's why we end up with the 6 dots. Now, when we do the formal charges, though, we're going to see how this probably isn't quite right. All right, so let me do the oxygens now with the single bonds. So up top, we have 6 for the oxygen. I'm just going to try to show these in purple. Hopefully it comes up a little bit better. And we've assigned this oxygen 2, 4, 6, 7. So that means this oxygen has a -1 charge. And the oxygen on the bottom, 1, 2, 3, 4, 5, 6, and 7 looks the same formal charge, -1. And we had talked about how sometimes you do have to have something that carries a -1 formal charge, but this is a molecule where there's no overall charge. It's not like the cyanate that had a -1 charge, so we knew something had to carry a -1. This is a compound with no charge. So the formal charges should all equal to 0. They have to. If it's a compound with 0 charge, all the formal charges should equal to 0. So then the unknown is the sulfur, right? That's the one we haven't done yet. And so for the sulfur like oxygen, right? I'm going to just kind of draw this over here. It has 6 valence electrons, and we've only assigned it 1, 2, 3, and 4. So it has a +2 formal charge. So sulfur here has a +2 formal charge. So then if I look at all my formal charges, 0 + 0 + 0 + 0, right? Those are all 0. -1 + -1 + 2, that all goes to 0. So that matches the charge on the molecule. So this is right. I did my formal charges correctly, because your formal charges should sum to the charge of the compound, which would be 0, or the ion if it's a polyatomic ion. Now, formal charges help us understand that sometimes we're going to expand the octet. And that happens when you have adjacent elements with a plus minus. All right, and what will happen here is we're going to have to expand the octet, but on what? Well, oxygen can't expand the octet. It has to go on the sulfur because sulfur is the row 3 element. If I look at my periodic table, right, there is a 3D. Sulfur doesn't use it by itself, but when it forms bonds, it can, because there is a 3D possibility. But with oxygen, there's no 2D. So oxygen can't expand the octet. So what'll happen is for the oxygen with the formal charge of -1, that's not great, right? We're not going to mess with the oxygens that have a formal charge of 0 because they're good, right? We want our formal charges to be 0. But the oxygen that's a -1, we don't want that. We want everything to be a 0 if we can. So we're going to take one of these lone pairs, right, where the -1 formal charge is, and we're going to move it to become a bonding pair. And then we're going to do that again. And the reason why we know that we're going to do it again is because we have a +2 center and a -1 and a -1. That means we're going to do this twice because it's +2, right? If it were +3, we would try to maybe do it 3 times, depending on what the structure was. So I'm going to do the same thing. I'm going to take one of these lone pairs on the oxygen with the formal charge of -1, and I'm going to move it to become a bonding pair. All right, so now what has happened, right? I think, well, I've ran out of paper is what has happened. Okay, so I'll do this on the back of another paper. All right, so I'll come back to the chlorine trifluoride. Sorry, I ran out of room. All right, so center is the sulfur. So start with that. The elements I had in the line, these didn't change. So the oxygen between the hydrogen and the sulfur, 2 lone pairs. Same thing on the left, 2 lone pairs, and then the terminal hydrogen with its single bond. So we didn't change anything here, right? So that all stays the same. The oxygen on top, though, we had a single bond, but we're moving that lone pair to become a bonding pair. So instead of a single bond, we're now going to have a double bond. And that oxygen, instead of having 3 lone pairs, it's now only going to have 2 lone pairs. So we took that lone pair and we made it the bonding pair. So now I'm just going to highlight it so you can trace where it went, right? So that's where that lone pair went. It became a bonding pair. Now, what did that do to the formal charge? So the formal charge here on this oxygen comes in with 6. And now we've assigned it 1, 2, 3, 4, 5, and 6. So now that formal charge on the oxygen has gone to 0. So that's good. Now, the same thing for the bottom. We moved a lone pair to become a bonding pair. So instead of just a single bond now, we're going to have a double bond. And now instead of 3 lone pairs, we're going to have 2 lone pairs, right? And so again, that lone pair, right, moved to become a bonding pair. Now the formal charge here starts with 6. We've assigned it 6. It's gone to 0. Now let's look at sulfur, right? Sulfur comes in with 6 and we've assigned it 1, 2, 3, 4, 5, and 6. So 6 minus 6 also has gone to 0. So for this structure, all formal charges are now 0, which is ideal, right? We always want that. And if you looked at this structure back in intro chem, you would have been like, no, that can't be right. Because when you look, sulfur, 2, 4, 6, 8, 10, 12. So if you're thinking about the octet rule, you're like, that's not possible. Sulfur can't have 12 electrons. So sulfur has expanded the octet. And the reason why it did that is to better the formal charges. Now, what's kind of strange about this is when we go into the next chapter and we start looking at geometries, it actually won't change the geometry of the structure. But again, what it would do is help us understand why these oxygen-sulfur bonds don't have all the same bond energy. If they were all just 4 single bonds, the energy would be the same throughout. But because these 2 are double and these 2 are single, they actually can see that the bond energy for this sulfur oxygen bond is not just a strict single, 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 single. So that's how we know. All right, so this formal charge, right? The expanded octet occurs when you have a center element here that can expand the octet. That's rule number one. It has to be possible. It has a positive formal charge, and its neighboring element has a negative formal charge. When that happens, a negative next to a positive, we can make it better by taking the lone pair on the negative, the terminal, and moving it into a bonding pair. So we're expanding the octet on the center element, but we're making those formal charges better. All right, so we end up here with the sulfuric acid and sulfate, right? Same thing, SO4 -2. We just take off the hydrogens, but the bonding pair here just becomes a lone pair. Anyway, that's another story. All right, so as I mentioned, bond length and bond order, that's how we know that it's not just the strict single bond all the way through for the oxygen and sulfur. So the bond order, all right, and this is easy, I think. Bond order is how many bonds it is. So like a single bond has an order of 1. If it's a double bond, right, like here, that would be a bond order of 2, triple bond order of 3. So that makes sense. Bond length, the distance in the bond, decreases with increasing bond order. So this oxygen sulfur single bond is longer than the double bond, right? And and we're not face to face, but when you get to play with the balls and stick models, you actually kind of feel that when you try to create a double bond or a triple bond, the atoms have to move closer together. Anyway, so the higher the bond order, the shorter the bond length. Now the bond energy, this made also complete sense to me. The energy required to break a bond is going to be way worse for a triple bond than a double bond, and way worse for a double bond than a single bond, right? That makes sense. You got more holding it together. There's more overlap. So it's going to be harder to break a double bond than a single bond. So that makes sense. Now, when you break bonds, that is an endothermic process, right? You have a stable, right? Remember, they have their octet, they're stable. So if you break that up, they're not going to be happy. So if you break a bond, you're going to have to put energy into it. All right, delta H for that process would be greater than 0. But when you form new bonds, right, then you're stabilizing those ions or elements, whatever it is, what type of bonding it is. And when new bonds are formed, then energy will be released. It'll be exothermic. And when you do the enthalpy of a reaction, like we did in the thermo chapter, you can get that in a couple of different ways. We did it through Hess's law, right? We did it through enthalpies of formation. You can also do it through bond energies. And what's interesting is you get the same answer each time. I always thought that was really cool. All right, so here's how we're going to look at this. We've got a combustion reaction, C2H4 ethene, and reacting it with oxygen creates CO2 and H2O. And we want to use the bond energies. This would be something that you'd find in the appendix in your book or in a chart or on the internet, right? You can look them up. And notice, right, the carbon oxygen bond versus just like single or double. Make sure you're careful with that in the chart. It'll tell you whether you're looking at a double bond or if it's just a carbon oxygen single bond, right? So make sure, like double bonds, right, have higher energies than single bonds for the most part as a general trend. But anyway, so in order for us to understand the bond energies that go into this reaction, we have to know what each of those Lewis structures look like. So for example, the C2H4, organic molecules really love to be symmetrical. So we've got what I call a double carbon center. And then on each of those carbons, we have an attached hydrogen. And if I look at my structure, I can tell carbon isn't happy because there's only 6 electrons here. So what I look at, if I go through the entire Lewis structure, each carbon brings in 4 valence electrons, so a total of 8 for the 2 carbons. Each hydrogen brings in 1, so 4 for the 4 hydrogens. So I have 12 electrons to work with. 2, 4, 6, 8, 10. So I've got 2 more. Both carbons need 2 more. So this is going to be a double bond. All right. And so now there's my 12 electrons, 2, 4, 6, 8, 10, 12. And now everybody has duet for hydrogen and octet for carbon, 2, 4, 6, 8 for this carbon. So that's my ethene structure. Oxygen we saw earlier, it's a double bond. All right, so I'm not doing the complete Lewis structures with all the lone pairs because they don't matter anyway when it comes to this. The carbon dioxide we saw earlier, it had 2 double bonds, right, 1 on each side. And then water is nice and easy. We'd have hydrogen, single bond to oxygen, single bond to hydrogen. All right, so that's what our molecules look like. So when I do this delta H, right, this thermochemical equation, what I want to look at first is what bonds do I have to break? All right, so bonds that we are going to break. All right, first thing is we got to break up this carbon-carbon double bond, right? So we got to break that up. Then I'm going to have to break up this carbon hydrogen single bond, but I've got to do that 1, 2, 3, 4 times. So times 4. Then I have to do the oxygen double bond, right? All of this has to be broken, right? So that's what I'm showing here. Like everything on the reactant side, I have to break it up. So I got to break up the carbon-carbon double bond, split that. I got to break up the carbon-hydrogen single bond 1, 2, 3, 4 times. And then that oxygen double bond, I also have to break that up, but I've got 3. I've got 3 of those in my balanced equation. So I'm going to have to multiply by 3 here. All right, so don't forget the coefficients. All right, so my carbon-carbon double bond, it says on the chart, 611, this would be in kilojoules per mole, so 1 mole, so kilojoules. The oxygen double bond is the 498, and again, I'd have to multiply that by 3. And the carbon hydrogen single bond, multiply that by 4. All right, so let me get out my calculator. The 414 times 4 is 1656, and the 498 times 3 is 1494. And then the 611. So let me add all of that together now. So 1494 plus 1656 plus 611. So 3,761. All right. And this is positive. This is endothermic, right? Because all of those bonds have to be broken. That's the energy I've got to put into this to even get this reaction to go, right? I got to get up that hill, break up all those bonds before I can start releasing energy as I form new bonds. All right, so now let's look at the bonds that are formed. All right, so that is everything on the product side. All right, so on the product side, we formed a carbon-oxygen double bond, but I had to have 2 per molecule, right? So 1, 2, and the coefficient of 2. So then I got to do times 2 again. So the carbon oxygen double bond of 736 is actually going to be in like times 4, right? Because we need to form this 1, 2 times 2. So 2 times 2 is where I'm getting a total of 4. The oxygen hydrogen single bond, I've got to do 2 per molecule, and there's 2 of them here. So 1, 2 times 2, also 4. So the hydrogen oxygen single bond is 464. And we're going to multiply that by 4. All right. So again, 1, 2, and then times 2. So a total of 4. Now, this is all exothermic. So let me get you the answer here. So we got 736 times 4, which is 2944. And add to that 464 times 4, which is 1856. And I get 4,800. All right, but this is going to be negative because all of those bonds are formed. So exothermic. So if I want to get my delta H overall, I have to put in 3,761 kilojoules to break up those bonds. But then I get out 4,800 with the release of energy from the formation of new bonds. So when I take that difference, I get a negative 1039 kilojoules. So that would be my net delta H for the reaction, negative 1039 kilojoules. All right, and the unit on there, it should have it on there, like on the chart. It was my mistake for not putting on, but these are always in kilojoules per mole. So that's what we do for looking at bond energies. You have to first tally all the energy put in to break up all the bonds, and then how much energy is released by forming those new bonds. And then it makes sense. Energy in, energy out, what's my net? And as long as we release more energy than we have to put in, overall, we have an exothermic reaction. And we know that combustion reactions are always exothermic, right? They always release a lot of energy. So there's a couple of those in the homework to practice. The chart is in the textbook. But that's it for the notes for this chapter. So chapter 10, what we did is we took some of the information we have in chapter 9, valence electrons, electronegativity. Then we look at bonding. In this chapter, we look at Lewis structures. We now understand formal charges and how they help us get the right Lewis structure. We also brought in the idea of an expanded octet, which is a little bit different from intro chem. When we look at these bond energies, this is kind of a one-hit wonder. It's just like this one little topic. We won't carry it forward, the bond energies, but it is something that's interesting to know. And then in the next chapter, now what we're going to do is, like I kept mentioning, is okay, how is it that the S and P, how do they overlap, right? How do you have a spherical orbital and electrons that are just on the P axis? How does that work? How do they overlap to where they share electrons? It doesn't make sense if they're not the same geometry, then how could they overlap? And so that's what we're going to look at in the next chapter, is how that works, the hybridization. So again, all just one big topic, right? So next week on Tuesday, that's what we're going to look at, chapter 11. The chapter 9 credit quiz is going to be due Tuesday at midnight, right? So you always have a week after we're done. So that's the next thing that's due for the lecture class, is the credit quiz for chapter 9. That'll be due Tuesday at midnight. Otherwise, that's it for me for today. If you have any questions for me, let me know. But otherwise, I hope you have a great weekend. Happy 4th. I can't believe it's already the 4th of July. Happy 4th. Stay safe. I'll see you back Tuesday. Okay, so I forgot to do, we had skipped over this molecule in the notes after we had done the sulfuric acid and we looked at the expanded the octet. We had this chlorine trifluoride that we were going to look at. So first thing is the center element. And again, symmetry is usually your friend. So you kind of think, oh, I got a single chlorine, that should probably go in the middle. And then I have the multiple fluorines, so that makes sense that that would go on the end. However, I will say that doesn't always work. 9 times out of 10, it does. But again, there's always ones that kind of throw you for a loop. So really what you want to do is always go back to your table and say, okay, fluorine is our most electronegative, so it can't go in the center, period. That means chlorine has to go in the center. So we know chlorine will go in the middle. And then I'll put fluorine on any 3 sides that we want. All right, now I'm going to go and look at my valence electrons. So valence electrons here, chlorine, group 7, fluorine, also group 7. So 3 fluorines means I really have 21 electrons from all 3 of those. Plus another 7 from the chlorine means I have 28 total valence electrons. Again, that's my number. Now, how many have I used? 2, 4, 6. I've used 6 electrons in those 3 bonds. So I have 22 electrons left over. All right, and now I go and look and see where they should go. All right, each of the fluorines have, at this point, only 2 electrons around them. So they would need 6 more to get to 8, right? We always, again, always trying to make the octet except hydrogen and boron, but otherwise that's always where we start. We always want to focus on making the octet. The chlorine in the middle has 3 bonds. So 2, 4, 6 needs 2 more to get to 8. So if I add all that together, I got 6, 2, 6, and 6, that's 20. And so this is opposite of the problem that we had before. All right, before we saw where if we don't have enough electrons, we have to increase the sharing. This is different. We have too many electrons. So now what do you do? All right, so that means when you have excess, you're going to have to expand the octet, right? Because everything we do with the math here is all about octet, 8, 8, 8, right? That's all what we're doing. So if we have excess electrons, in this case, we have 2, we have to expand the octet on something, right? And then if I look at my periodic table, I know that fluorine can't expand the octet because it's a row 2 element, right? And there's only 2s and 2b, there's no 2d. So it has to go on the chlorine. So for each of the fluorines, actually, let me start over. All right, I'm going to have 3 lone pairs to complete the octet. And so each fluorine has 3 lone pairs and then a bonding pair. And then the chlorine, we thought would just need 2 more electrons to complete the octet, but we have 2 extra electrons. So it actually ends up again with the expanded octet. So we expanded the octet on the chlorine because again, chlorine is the row 3 element. It can go past 8 because there are 3D orbitals, right? It's in row 3. So there are 3D orbitals that it can tap into. So when I look at my formal charges here, this is going to tell me also that I've got the correct structure. So when I look at my formal charges, all of the fluorines look the same. So we'll just do this once. They come in with 7 valence electrons, and we've assigned it 1, 2, 3, 4, 5, 6, 7. So 7 minus 7, we have a total net of 0. The chlorine also group 7. And now how many have we assigned it? 1, 2, 3, 4, 5, 6, and 7. So chlorine has been assigned 7, also formal charge of 0. So that tells us we got the right structure. All the formal charges of 0 are 0. That's always what we want. What's peculiar though about this structure is that we had to expand the octet. So when we think about what we learned in intro, everything was about the octet rule, and we didn't worry about formal charges. Now we worry about formal charges to either A, help us pick the correct structure, given 3 possibilities, right? That was the first thing we did. Or B, if we're saying, okay, well, I've got extra electrons here, where should I put them? Well, it made sense. It can't go on fluorine because they can't expand the octet, but you can always do your structure and then look at formal charges to make sure that you've got it. So first thing is focus on the octet. We're still always trying to get to the octet, but there are times when you have that exception. And again, that will only happen if you have a row 3 element, row 4, row 5, right? Something that can tap into D orbitals in that energy shell. All right.
So we